right, so today we are going to talk about topic 4.7, which is LHospitals Rule. All right, so those of you who have had French know that that's how you would say it. It's not Le Hospital, it's L'Hôpital. And you guys are going to love L'Hôpitals Rule because all those, not all of them, but a lot of those limits that we did at the beginning of the year, we can actually do easier using L'Hôpitals Rule. Now, I couldn't teach it to you then because you didn't know how to take a derivative, but now you pretty much know how to take a derivative of any function that I can throw at you. So we're going to use L'Hôpitals Rule when we can. So when a limit produces indeterminate form, and if you guys remember, it's been a while, but indeterminate form is when we are going to get 0 over 0 or some kind of infinity over some kind of infinity. You can use L'Hôpitals Rule. All right, and L'Hôpitals Rule tells us that if we have the limit as x approaches c of f of x over g of x, and that gives us 0 over 0 or infinity over infinity, what we can do is then find the limit as x approaches c of f prime of x over g prime of x. So basically just find the derivative and of the numerator and the denominator, and then try it again. Try plugging in c again and see if you get 0 over 0. If you don't, you get like 2 over 3 or something like that, then you have the value of the limit. And like I said, I kind of threw an infinity over there. If you have limit as x approaches infinity of f of x over g of x, and you get infinity over infinity or negative infinity over negative infinity or something like that, you can then find the limit as x approaches infinity of f prime of x over g prime of x. And you can keep finding the derivatives. Like if you keep getting indeterminate form, find the derivative again, until eventually maybe you can plug in a value, plug in infinity and get just a value instead of something indeterminate. All right, so let's look at some examples. So for example 1, we're going to evaluate these limits. In A, we have the limit as x approaches 0 of e to the 2x minus 1 over x. All right, so now we would never ever say that this limit equals 0 over 0 because that's not true. It's actually equal to a value that we're going to find in a second. But whenever we plug 0 in for the numerator, we get e to the 0 minus 1 or 1 minus 1, which is 0. And then when we plug 0 into the denominator, we also get 0. So it give you 0 over 0. So we can use L'Hôpitals Rule and now find the limit as x approaches 0 and then just find the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator, or if you guys remember, the derivative of e to something is going to still be that e to that something. But then we multiply by the derivative of that something, and the derivative of 2 to the x is just 2. And then the denominator, the derivative of 1 is just 1. So now, if I plug in the 0, I get e to the 2 times 0 times 2 over 1, or just 1 times 2, which is 2. All right, so if you get indeterminate form, you can just find the derivative of the numerator, find the derivative of the denominator, and then plug in again and see what you get. All right, so let's look at b. For b, we have the limit as x approaches infinity of the natural log of x over x. So if I plugged in infinity to the numerator, the natural log of infinity is still infinity. And then the denominator is still going to be infinity. So that's indeterminate form. So we can do LHospitals Rule, where we'll find the derivative of the numerator, and the derivative of the natural log of x is 1 over x. And then we find the derivative of the denominator. The derivative of x is just 1. All right, then we can plug in our infinity. So we get 1 over infinity over 1, which we don't need to write. And anytime you have 1 divided by infinity, that's just 0. All right, and let's look at c. For c, we have the limit as x approaches infinity of 3x squared plus 4x minus 5 over 6x squared minus 7x. Okay. So if I plug in infinity in the numerator, infinity squared plus a whole bunch of stuff is still going to be infinity, and the denominator is going to also be infinity. So I can find the derivative. So the limit as x approaches infinity of 6x plus 4 over 12x minus 7. All right, then if I plug in an infinity again, I'm still going to get infinity over infinity. So this is when you can do LHospitals Rule a second time. All right, so it's still going to be the limit as x approaches infinity. And then the derivative of the numerator is just 6 now. The derivative of the denominator is just 12. All right, and then there's no x left. There's nowhere to plug in the infinity. So that just gives you 6 over 12, or 1/2. Now, sometimes whenever you're doing these limits with L'Hopital's rule, you can still get infinity as an answer. So, like if you end up with, you plug in and you get infinity over 2, that's going to be infinity. Is that the representation of that limit? It's not really a limit. Technically, it doesn't exist if you get infinity, but don't be surprised if it doesn't. Some of the ones you do on your own don't work out perfectly. They reduce down to nothing. All right, and then let's look at D. For D, we have the limit as x approaches 0 of sine of 2x over 3x. All right, so when I plug in 0, the sine of 0 is 0, and then 3 times 0 is 0, so I can use L'Hopital's rule. All right, so when I find the derivative of something, it's going to be the cosine of that something times the derivative of that something, and the derivative of 2x is just 2, so I'm going to multiply by that 2 in the front. All right, and then the derivative of 3x is just 3. Okay, so I'm ready to plug in my 0. Okay, so then the cosine of 0 is 1. So that limit is going to be 2/3. Now we used to do all this kind of crazy manipulation with ones like that, but now we can use L'Hopital's rule. All right, so don't just assume you can always do L'Hopital's rule. Remember, you have to get indeterminate form to be able to use it. So the directions on your assignment are to use L'Hopital's rule if you can. on page 564, 12, 16, 22 through 24, 26, 28, 36, and 38.